Welcome to your peaceful journey through artificial intelligence. Tonight, we will explore 50 essential AI concepts designed specifically for bedtime learning. Each explanation is crafted to be both informative and deeply relaxing, helping you understand the fascinating world of artificial intelligence while preparing your mind for restful sleep. From basic machine learning principles to advanced neural networks, you will discover how AI shapes our modern world. Every concept builds naturally on the previous one, creating a gentle flow of knowledge that soothes rather than stimulates. Find your most comfortable position, close your eyes, and allow these AI insights to guide you toward peaceful rest. Let us begin this calming exploration of artificial intelligence together. Concept 1. Artificial intelligence. Artificial intelligence represents the remarkable ability of machines to perform tasks that typically require human intelligence. Think of it as teaching computers to think, reason, and make decisions in ways that mirror our own cognitive processes. At its core, artificial intelligence is about creating systems that can perceive their environment, process information, learn from experience, and take actions to achieve specific goals. The journey of artificial intelligence began with simple rule-based systems that could follow predetermined instructions. Imagine a digital assistant that knows exactly what to do when you ask for the weather. However, modern AI has evolved far beyond these basic responses. Today's artificial intelligence systems can recognize faces in photographs, translate languages instantly, recommend movies you might enjoy, and even drive cars through busy city streets. What makes artificial intelligence truly fascinating is its ability to improve over time. Unlike traditional computer programs that perform the same tasks repeatedly without change, AI systems learn from each interaction. They analyze patterns in data, identify relationships between different pieces of information, and adjust their behavior based on new experiences. This learning capability allows AI to become more accurate and efficient with practice. The beauty of artificial intelligence lies in its versatility. The same underlying principles that help a computer recognize speech can be applied to medical diagnosis, financial analysis, or creative writing. As you rest tonight, consider how this technology quietly enhances countless aspects of our daily lives, from the smartphone in your pocket to the streaming service that knows exactly what show might help you unwind. Concept 2. Machine learning. Machine learning forms the beating heart of modern artificial intelligence, representing a fundamental shift in how we approach problem solving with computers. Rather than programming explicit instructions for every possible scenario, machine learning allows systems to discover patterns and make predictions by analyzing vast amounts of data. Think of it as teaching a computer to learn from experience, much like how children develop understanding through observation and practice. The process begins with training data, which serves as the foundation for learning. Imagine showing a child thousands of pictures of different animals while telling them which animal appears in each image. Similarly, machine learning systems examine countless examples to identify the subtle characteristics that distinguish cats from dogs, emails from spam, or fraudulent transactions from legitimate ones. Through this exposure, the system gradually builds an internal understanding of the patterns that define each category. What makes machine learning particularly powerful is its ability to handle complexity that would overwhelm traditional programming approaches. Consider the challenge of recognizing handwritten text. Writing a traditional computer program to handle every possible variation in handwriting would be nearly impossible. However, a machine learning system can examine millions of handwriting samples and automatically discover the patterns that allow accurate recognition. The learning process involves continuous refinement. When a machine learning system makes a prediction, it receives feedback about whether that prediction was correct. This feedback helps the system adjust its internal parameters, gradually improving its accuracy over time. As you drift into peaceful sleep, imagine these digital minds quietly learning and growing stronger, becoming better equipped to assist humanity with each passing moment. Concept 3. Algorithms. Algorithms represent the fundamental building blocks of artificial intelligence, serving as step-by-step recipes that guide computers through complex decision-making processes. Think of an algorithm as a detailed instruction manual that tells a computer exactly how to solve a specific problem or accomplish a particular task. Just as a cooking recipe provides precise steps to create a delicious meal, algorithms provide precise steps for computers to process information and reach intelligent conclusions. Every digital interaction in your daily life involves countless algorithms working behind the scenes. When you search for information online, algorithms determine which results appear first. When you navigate using a map application, algorithms calculate the fastest route to your destination. When you receive personalized recommendations for music or videos, algorithms analyze your preferences to suggest content you might enjoy. These mathematical procedures form the invisible infrastructure that powers our connected world. The elegance of algorithms lies in their logical structure. Each algorithm breaks down complex problems into smaller, manageable steps that can be executed systematically. Consider how you might organize a large collection of books alphabetically. You would likely compare titles, group similar letters together, and arrange them in order. Algorithms follow similar logical patterns, but with mathematical precision that allows computers to process millions of comparisons in seconds. Modern artificial intelligence relies on increasingly sophisticated algorithms that can adapt and improve their performance. These adaptive algorithms learn from experience, adjusting their approach based on new information and feedback. As you rest tonight, countless algorithms continue their quiet work, sorting through data, making predictions, and optimizing systems to create a smoother, more intelligent world for tomorrow. Concept 4. Data. Data serves as the essential fuel that powers every artificial intelligence system, representing the raw material from which machines extract knowledge and understanding. Think of data as the digital equivalent of life experiences that help humans learn and make informed decisions. Just as you rely on memories and observations to navigate daily challenges, artificial intelligence systems depend on vast collections of data to recognize patterns, make predictions, and improve their performance over time. The diversity of data in our modern world is truly remarkable. Every click on a website, every photograph taken, every purchase made, and every message sent contributes to the ever-growing ocean of digital information. This data comes in many forms, including numbers, text, images, sounds, and videos. Social media posts reveal human emotions and preferences, sensor readings from smartphones track movement and location, and transaction records show spending patterns and economic trends. What makes data particularly valuable for artificial intelligence is its ability to reveal hidden patterns and relationships. Individual pieces of data might seem unremarkable, but when analyzed collectively, they tell compelling stories. For example, millions of weather measurements collected over decades help AI systems predict future climate patterns. Similarly, analyzing countless medical records enables AI to identify early warning signs of diseases that human doctors might miss. The quality and quantity of data directly influence the effectiveness of artificial intelligence systems. Clean, well-organized data leads to more accurate predictions and better decision-making, while poor quality data can mislead AI systems and produce unreliable results. As you prepare for sleep, consider how your own digital footprint contributes to this vast repository of human knowledge, helping create smarter systems that benefit everyone. Concept 5. Pattern recognition. Pattern recognition represents one of the most fundamental and fascinating capabilities of artificial intelligence, enabling machines to identify meaningful structures and relationships within complex information. This ability mirrors one of the most essential human cognitive skills, our natural tendency to recognize faces, understand speech, and make sense of the world around us by identifying familiar patterns. When AI systems perform pattern recognition, They are essentially discovering the hidden order that exists within seemingly chaotic data. Consider how effortlessly you recognize a friend's face in a crowded room or identify your favorite song within the first few notes. Your brain accomplishes these remarkable feats by comparing new sensory input against patterns stored in memory. Artificial intelligence systems work similarly, but with the ability to process vast amounts of information simultaneously and identify patterns that might be invisible to human perception. The applications of pattern recognition in artificial intelligence are virtually limitless. Medical AI systems examine thousands of medical images to identify subtle patterns that indicate disease. Financial systems analyze spending patterns to detect fraudulent transactions. Recommendation engines study your behavior patterns to suggest products or content you might enjoy. Voice recognition systems identify the unique patterns in your speech that distinguish your words from background noise. What makes pattern recognition particularly powerful is its ability to find relationships across different types of information. Modern AI systems can recognize patterns that span multiple dimensions, connecting visual features with audio characteristics, or linking behavioral patterns with environmental factors. As you settle into peaceful rest, imagine these digital pattern detectors working tirelessly through the night, uncovering insights and connections that will make tomorrow's technology more helpful and intuitive. Concept 6. Training and testing. Training and testing form the essential foundation of artificial intelligence development, representing a systematic approach to teaching machines how to make accurate decisions and verify their reliability. This process closely mirrors how humans acquire new skills through practice and evaluation. Just as a musician practices scales before performing a concert, or a student studies before taking an examination, AI systems must undergo rigorous training and testing phases to ensure they can perform effectively in real-world situations. The training phase involves exposing artificial intelligence systems to vast amounts of carefully prepared examples. During this crucial period, the AI system analyzes patterns, learns from mistakes, and gradually improves its ability to make correct predictions or classifications. Think of this as an intensive learning experience where the AI encounters thousands or even millions of scenarios, each one teaching valuable lessons about the task it needs to master. Testing serves as the quality assurance phase, where AI systems demonstrate their learned capabilities on completely new, unseen data. This evaluation process is critical because it reveals whether the system has truly learned generalizable skills or simply memorized specific examples. A well-tested AI system should perform accurately on new situations that it has never encountered before, proving that it has developed genuine understanding rather than rote memorization. The relationship between training and testing requires careful balance. Too little training results in poor performance, while excessive training on limited data can lead to overly specialized systems that fail when faced with new situations. As you drift towards sleep, consider how this patient process of learning, devaluation, creates the reliable AI systems that enhance our daily lives, from accurate weather predictions to personalized healthcare recommendations. Concept 7. Automation. Automation through artificial intelligence represents the transformation of repetitive, time-consuming tasks into seamless, efficient processes that require minimal human intervention. This concept embodies the promise of technology to free humans from mundane activities, allowing us to focus on creative, strategic, and meaningful work that leverages our unique capabilities. Think of automation as having an incredibly diligent assistant who never gets tired, never makes mistakes due to fatigue, and can work continuously to handle routine responsibilities. The beauty of AI-driven automation lies in its intelligence and adaptability. Unlike traditional automation that simply follows predetermined steps, artificial intelligence brings decision-making capabilities to automated processes. Smart automation systems can analyze situations, adapt to changing conditions, and make informed choices about the best course of action. For example, automated customer service systems can understand natural language, interpret customer emotions, and provide personalized responses that feel genuinely helpful rather than robotic. Modern automation extends far beyond simple repetitive tasks. Intelligent systems now handle complex processes like managing supply chains, optimizing energy consumption in smart buildings, and coordinating transportation networks. These sophisticated automation systems continuously monitor multiple variables, predict potential problems, and make real-time adjustments to maintain optimal performance. They work like invisible conductors orchestrating complex symphonies of interconnected systems. The impact of intelligent automation on daily life continues to expand in remarkable ways. Your smartphone automatically adjusts screen brightness based on ambient light, your home thermostat learns your schedule to optimize comfort and energy efficiency, and your email system automatically filters spam to protect your productivity. As you prepare for restful sleep, countless automated systems continue their quiet work, maintaining the infrastructure and services that make modern life comfortable and convenient. Concept 8. Computer vision. Computer vision empowers machines with the remarkable ability to see, interpret, and understand visual information from the world around them. This fascinating field of artificial intelligence attempts to replicate and enhance human visual perception, enabling computers to extract meaningful insights from images and videos. Think of computer vision as giving machines a sophisticated pair of digital eyes that can not only capture visual information, but also comprehend what they are seeing with incredible precision and speed. The process of computer vision involves multiple layers of analysis, starting with basic detection of edges and shapes, then progressing to recognition of objects, faces, and complex scenes. Modern computer vision systems can identify thousands of different objects, understand spatial relationships between items, track movement over time, and even interpret human emotions from facial expressions. These capabilities enable applications that seemed like science fiction just decades ago. The practical applications of computer vision have become deeply integrated into our daily lives. Your smartphone camera automatically focuses on faces and adjusts lighting for better photos. Self-driving cars use computer vision to navigate roads safely, identifying pedestrians, other vehicles, traffic signs, and road conditions. Medical imaging systems help doctors detect diseases by analyzing X-rays, MRIs, and other diagnostic images with superhuman accuracy and consistency. What makes computer vision particularly impressive is its ability to process visual information much faster than human perception while maintaining remarkable accuracy. These systems can simultaneously analyze multiple video streams, detect subtle changes that might escape human notice, and provide instant alerts about important events. As you close your eyes tonight, imagine the countless computer vision systems standing silent watch, monitoring security cameras, inspecting manufacturing processes, and ensuring safety across numerous industries while the world sleeps peacefully. Concept 9. Natural language processing. Natural language processing represents one of the most ambitious goals in artificial intelligence, teaching machines to understand, interpret, and generate human language with all its complexity, nuance, and beauty. This field bridges the gap between human communication and computer understanding, enabling machines to process the rich, contextual, and often ambiguous nature of human speech and writing. Think of NLP as creating digital translators that can not only convert words between languages, but also understand meaning, emotion, and intent behind human expression. The challenge of natural language processing stems from the incredible complexity of human communication. Unlike computer programming languages that follow strict rules and syntax, human language is filled with idioms, sarcasm, cultural references, and contextual meanings that can change dramatically based on situation and speaker. When you say something is cool, you might mean temperature, approval, or emotional detachment depending on the context. NLP systems must navigate these linguistic complexities to truly understand human communication. Modern natural language processing systems have achieved remarkable capabilities that transform how we interact with technology. Virtual assistants understand spoken requests and provide helpful responses. Translation services instantly convert text between dozens of languages while preserving meaning and tone. Content analysis systems can read thousands of documents to extract key insights, summarize lengthy reports, and identify important themes that would take humans weeks to analyze. The applications of NLP continue expanding into new domains, from analyzing social media sentiment to helping diagnose mental health conditions through speech patterns, from generating creative writing to providing personalized education based on individual learning styles. As you drift into sleep, consider how these language understanding systems work continuously to break down communication barriers, making information more accessible and human-computer interaction more natural and intuitive. Concept 10. Expert systems. Expert systems represent early artificial intelligence pioneers that captured human expertise and decision-making processes in specialized domains, creating digital consultants that could provide knowledgeable advice and solutions. These systems embody the ambitious goal of preserving and sharing the wisdom of human experts, making specialized knowledge available to anyone who needs it. Think of expert systems as having access to a panel of world-renowned specialists who can analyze complex problems and provide thoughtful recommendations based on decades of accumulated experience. The foundation of expert systems lies in their knowledge base, which contains carefully encoded rules and facts that represent how human experts approach problems in their field. These systems work by asking relevant questions, gathering information about the current situation, and then applying logical reasoning to reach conclusions that mirror how experienced professionals would think through the same challenges. Unlike general-purpose AI systems, expert systems focus deeply on specific domains where their knowledge and reasoning capabilities can provide exceptional value. Medical diagnosis systems exemplify the power of expert systems, helping doctors consider rare conditions, drug interactions, and treatment options that might not immediately come to mind. Financial planning systems guide investment decisions by analyzing market conditions, risk tolerance, and long-term goals. Engineering design systems help create optimal solutions while considering safety regulations, material properties, and cost constraints. These specialized systems serve as invaluable second opinions and knowledge repositories. The legacy of expert systems continues influencing modern artificial intelligence development, emphasizing the importance of domain expertise and logical reasoning. While contemporary AI systems have become more flexible and learning-oriented, the core principle of capturing and sharing human knowledge remains fundamental to creating useful AI applications. As you settle into peaceful rest, imagine these digital experts standing ready to share their accumulated wisdom, helping solve problems and make informed decisions across countless specialized fields. Concept 11. Supervised learning. Supervised. Learning represents the most intuitive approach to teaching artificial intelligence, closely mirroring how humans learn through guidance and feedback from teachers or mentors. In this learning method, AI systems receive carefully labeled examples that show both the input information and the correct output or answer. Think of supervised learning as studying with a patient tutor who provides both practice problems and their solutions, allowing the student to understand the relationship between questions and correct responses. The process begins with training data that contains thousands or millions of examples where the desired outcome is already known. For instance, when teaching a system to recognize handwritten digits, researchers provide images of handwritten numbers alongside labels indicating which digit each image represents. The AI system analyzes these paired examples, gradually learning to identify the visual patterns that distinguish a handwritten 3 from a handwritten 8. This methodical exposure to correct examples builds the foundation for accurate predictions. What makes supervised learning particularly powerful is its ability to generalize from specific examples to broader understanding. After studying numerous labeled examples, the system develops internal rules that help it make accurate predictions about completely new, unlabeled data. This capability allows supervised learning systems to diagnose diseases from medical images they have never seen before, translate languages they were not explicitly programmed for, and recognize speech from speakers with unique accents or speaking styles. The applications of supervised learning span virtually every industry and domain where prediction accuracy is crucial. Email systems learn to distinguish spam from legitimate messages. Financial systems learn to detect fraudulent transactions. And recommendation engines learn to suggest products that match individual preferences. As you drift toward peaceful sleep, imagine these patient digital students continuing their studies, gradually becoming more knowledgeable and helpful with each new example they encounter. Concept 12. Unsupervised learning. Unsupervised learning embodies the fascinating ability of artificial intelligence systems to discover hidden patterns and structures within data without explicit guidance or labeled examples. This approach mirrors the natural human tendency to observe the world and independently notice relationships, categories, and underlying organizing principles. Think of unsupervised learning as a curious explorer venturing into uncharted territory, equipped only with observational skills and the ability to recognize when things belong together or follow similar patterns. Unlike supervised learning, which relies on teacher-provided answers, unsupervised learning systems must find their own insights within raw, unlabeled data. These systems examine vast collections of information, looking for natural groupings, recurring themes, or underlying structures that might not be immediately obvious to human observers. The process resembles how you might organize a collection of photographs by naturally grouping them into categories like family gatherings, vacations, or seasonal events, even without explicit instructions to do so. The power of unsupervised learning lies in its ability to reveal unexpected insights and discover relationships that humans might overlook. These systems can analyze customer behavior data to identify distinct shopping patterns, examine genetic information to discover new disease subtypes, or study social media posts to understand emerging cultural trends. The discoveries often surprise researchers, revealing connections and categories that were not anticipated when the analysis began. Market research teams use unsupervised learning to segment customers into meaningful groups based on purchasing behavior and preferences. Scientists apply these techniques to analyze complex datasets in astronomy, biology, and climate research, uncovering new phenomena and relationships. As you settle into restful sleep, consider how these autonomous digital detectives work tirelessly through the night, sifting through information to uncover valuable insights that advance human knowledge and understanding. Concept 13. Reinforcement learning. Reinforcement learning represents perhaps the most dynamic and interactive approach to artificial intelligence training, where systems learn through trial and error while receiving rewards for successful actions and consequences for poor decisions. This method closely resembles how children learn to navigate the world by experimenting with different behaviors and adjusting their approach based on positive or negative outcomes. Think of reinforcement learning as teaching AI through experience rather than instruction, allowing systems to develop strategies and skills through direct interaction with their environment. The foundation of reinforcement learning rests on the concept of an agent that takes actions within an environment and receives feedback in the form of rewards or penalties. The AI system begins with no knowledge of what constitutes good or bad behavior, instead discovering effective strategies through countless interactions and experiments. Over time, the system learns to associate certain actions with positive outcomes, gradually developing sophisticated strategies that maximize rewards while minimizing negative consequences. What makes reinforcement learning particularly compelling is its ability to discover novel solutions that human programmers never explicitly taught or anticipated. These systems often develop creative strategies that surpass human performance in complex domains. Game-playing AI systems have revolutionized strategic thinking in chess, Go, and video games by discovering unconventional tactics that professional human players later adopted. Similarly, robotic systems learn to walk, manipulate objects, or navigate obstacles through patient experimentation rather than programmed instructions. The applications of reinforcement learning extend far beyond games into practical domains like autonomous vehicle navigation, resource optimization, and personalized education systems that adapt to individual learning styles. These systems continuously refine their approaches based on real-world feedback, becoming more effective with every interaction. As you prepare for sleep, imagine these persistent learners practicing and improving their skills throughout the night, developing better strategies to serve humanity more effectively. Concept 14. Deep learning. Deep learning represents a revolutionary advancement in artificial intelligence that attempts to mimic the layered structure of the human brain through artificial neural networks with multiple levels of interconnected processing units. This approach transforms how machines understand complex information by building understanding gradually through successive layers of analysis, much like how human perception progresses from recognizing basic shapes and colors to understanding complete scenes and their meaning. Think of deep learning as creating artificial minds with multiple levels of understanding, each layer building upon the insights of the previous one. The architecture of deep learning systems consists of numerous interconnected layers, each designed to extract increasingly sophisticated features from input data. The initial layers might detect simple patterns like edges or basic shapes in images, while deeper layers combine these simple features into more complex representations like faces, objects, or entire scenes. This hierarchical processing allows deep learning systems to understand information at multiple levels of abstraction simultaneously, creating rich and nuanced understanding of complex data. What makes deep learning particularly powerful is its ability to automatically discover the most important features within data without human guidance. Traditional machine learning approaches required experts to manually specify which characteristics were most relevant for analysis. Deep learning systems eliminate this bottleneck by learning to identify the most informative patterns through the training process itself, often discovering features that human experts never considered. The impact of deep learning has transformed numerous fields, including computer vision, natural language processing, and speech recognition. These systems power the image recognition capabilities in your smartphone, enable real-time language translation, and drive advances in medical diagnosis and scientific research. As you drift into peaceful sleep, countless deep learning systems continue processing information through their multiple layers, gradually developing richer understanding that will enhance tomorrow's technological capabilities. Concept 15. Neural networks. Neural networks form the foundational architecture that enables artificial intelligence systems to process information in ways that loosely parallel the structure of biological brains. These interconnected networks of artificial neurons work together to transform input information through multiple stages of processing, creating systems capable of learning complex patterns and making sophisticated decisions. Think of neural networks as creating simplified digital versions of the neural pathways in your brain, where information flows through interconnected nodes that each contribute to the overall understanding and decision-making process. Each artificial neuron in the network receives input signals, processes them according to learned parameters, and passes the results to other neurons in subsequent layers. This process mirrors how biological neurons communicate through electrical and chemical signals though artificial neural networks operate with mathematical calculations rather than biological processes. The strength of connections between neurons can be adjusted during learning, allowing the network to adapt its behavior based on experience and feedback. The power of neural networks lies in their ability to learn complex, non-linear relationships within data that would be difficult or impossible to program explicitly. These networks excel at tasks that require pattern recognition, such as identifying objects in photographs, understanding spoken language, or predicting future trends based on historical data. The collective behavior of hundreds or thousands of artificial neurons creates emergent intelligence that surpasses what any individual component could achieve alone. Modern neural networks have evolved into sophisticated architectures designed for specific types of problems, from image processing to language understanding to game playing. These systems continue to grow in complexity and capability, with some networks containing billions of parameters that work together to process information. As you settle into restful sleep, imagine these vast networks of artificial neurons quietly processing information, their interconnected pathways creating the digital intelligence that enhances countless aspects of modern life. Concept 16. Backpropagation. Backpropagation represents the fundamental learning mechanism that enables neural networks to improve their performance by systematically adjusting their internal parameters based on the mistakes they make during training. This elegant mathematical process works backwards through the network, calculating how much each connection contributed to errors in the final output, and adjusting these connections accordingly. Think of backpropagation as a patient teacher who carefully analyzes each mistake, traces it back to its source, and provides specific guidance on how to avoid similar errors in the future. The process begins when a neural network makes a prediction that differs from the desired output, creating an error signal that needs to be addressed. Rather than making random adjustments, backpropagation calculates the precise contribution of each neuron and connection to this error. Starting from the output layer and working backwards through the network, the algorithm determines how much each parameter should be modified to reduce similar errors in future predictions. This systematic approach ensures that learning is both efficient and directed toward meaningful improvements. What makes backpropagation particularly remarkable is its ability to assign responsibility for errors across potentially millions of parameters in complex neural networks. The algorithm uses mathematical principles from calculus to calculate gradients that indicate both the direction and magnitude of necessary adjustments for each parameter. This precise mathematical guidance allows neural networks to learn from their mistakes in a coordinated fashion, with all parts of the network working together toward improved performance. The discovery and refinement of backpropagation has been crucial to the success of modern artificial intelligence. Without this systematic learning mechanism, neural networks would struggle to improve beyond random performance levels. Today, backpropagation enables everything from image recognition systems to language models to continuously refine their capabilities. As you drift towards sleep, imagine these digital learning systems patiently analyzing their mistakes and making tiny adjustments that gradually lead to better understanding and more accurate predictions. Concept 17. Gradient descent. Gradient descent serves as the mathematical compass that guides artificial intelligence systems toward optimal performance by systematically finding the best possible values for millions of parameters within neural networks. This optimization process resembles a patient hiker navigating through mountainous terrain in dense fog, using only the slope of the ground beneath their feet to guide them toward the lowest valley. Think of gradient descent as providing AI systems with an internal sense of direction that helps them continuously improve their decision-making capabilities. The fundamental principle behind gradient descent involves calculating the mathematical gradient, which indicates the steepest direction of change for any given parameter in the system. When a neural network makes predictions, gradient descent examines how small changes to each parameter would affect the overall performance. If increasing a particular parameter would improve results, the algorithm moves in that direction. If decreasing it would be better, the algorithm adjusts accordingly. This process continues iteratively, with the system taking small steps toward better performance. What makes gradient descent particularly elegant is its ability to handle optimization problems involving millions or even billions of parameters simultaneously. The algorithm calculates gradients for all parameters and updates them in coordination, ensuring that the entire system moves toward improved performance in a unified manner. Modern variations of gradient descent include sophisticated techniques that adjust the step size dynamically, maintain momentum to avoid getting stuck in local minima, and adapt the learning rate for different parameters based on their individual characteristics. The applications of gradient descent extend beyond neural networks to virtually every machine learning algorithm that requires parameter optimization. From simple linear regression to complex deep learning systems, gradient descent provides the mathematical foundation for continuous improvement. As you prepare for peaceful rest, countless gradient descent algorithms work through the night, making tiny adjustments that incrementally improve AI systems and bring them closer to optimal performance. Concept 18. Overfitting. Overfitting represents one of the most common and challenging problems in artificial intelligence development, occurring when systems become so specialized to their training data that they lose the ability to generalize to new situations. This phenomenon resembles a student who memorizes textbook answers so thoroughly that they can not apply their knowledge to solve novel problems on an exam. Think of overfitting as the digital equivalent of becoming too narrowly focused, where an AI system develops an encyclopedic knowledge of specific examples but fails to understand the broader principles that would enable flexible problem solving. The root cause of overfitting lies in the tension between complexity and generalization that exists in all learning systems. When artificial intelligence models have too much capacity relative to the amount of training data available, they begin to memorize specific details and noise rather than learning meaningful patterns. These overfitted systems perform exceptionally well on familiar training examples, but struggle dramatically when confronted with new data that differs even slightly from their training experience. Detecting overfitting requires careful monitoring of system performance on both training data and separate validation data that the system has never seen during training. A healthy learning system should perform similarly on both datasets, indicating that it has learned generalizable patterns rather than specific memorized examples. When performance on training data continues improving, while performance on validation data begins declining, this divergence signals that overfitting has begun to occur. Preventing overfitting involves various strategies, including collecting more diverse training data, reducing model complexity, implementing regularization techniques that penalize excessive specialization, and using early stopping to halt training before overfitting begins. These approaches help maintain the delicate balance between learning meaningful patterns and preserving the flexibility needed for good performance on new problems. As you settle into sleep, consider how the challenge of overfitting reflects the broader wisdom of maintaining balance between specialization and adaptability in all learning endeavors. Concept 19. Feature engineering. Feature engineering represents the crucial art and science of transforming raw data into meaningful representations that artificial intelligence systems can effectively learn from and understand. This process involves carefully selecting, modifying, and creating input variables that highlight the most important patterns and relationships within data, while filtering out irrelevant noise and distractions. Think of feature engineering as translating complex real-world information into a language that machines can comprehend, much like how a skilled interpreter bridges communication between speakers of different languages. The success of many artificial intelligence projects depends heavily on the quality of feature engineering, as even the most sophisticated algorithms cannot extract insights from poorly prepared data. Effective feature engineering requires deep understanding of both the problem domain and the characteristics of the data being analyzed. For example, when analyzing text documents, feature engineers might create variables representing word frequency, sentence length, emotional tone, or grammatical complexity. When working with time series data, they might extract features related to trends, seasonality, or periodic patterns that occur at regular intervals. The process often involves creative thinking and domain expertise to identify non-obvious relationships that might be valuable for machine learning systems. Skilled feature engineers combine multiple raw variables to create new, composite features that capture interactions and relationships not apparent in individual measurements. They might combine location data with weather information to predict transportation delays, or merge customer demographic data with purchase history to identify buying patterns that inform marketing strategies. Modern deep learning systems have partially automated feature engineering through their ability to learn hierarchical representations directly from raw data. However, thoughtful feature engineering remains valuable for improving performance, reducing computational requirements, and creating more interpretable models. As you drift toward restful sleep, imagine these data artists working quietly through the night, crafting elegant representations that help artificial intelligence systems better understand and serve human needs. Concept 20. Cross-validation. Cross-validation serves as the rigorous quality assurance process that ensures artificial intelligence systems will perform reliably when deployed in real-world applications. This systematic evaluation technique addresses the fundamental challenge of estimating how well a trained model will generalize to new, unseen data by creating multiple training and testing scenarios using the available dataset. Think of cross-validation as conducting multiple dress rehearsals before a theatrical performance, with each rehearsal using different audience members to ensure the actors can adapt their performance to various situations. The most common approach, known as k-fold cross-validation, divides the available data into k-equal portions or folds. The system then undergoes k separate training and testing cycles, with each cycle using a different fold as the test set, while training on the remaining data. This process provides k different estimates of system performance, which can be averaged to obtain a more robust and reliable assessment than would be possible with a single train test split. The variation across these estimates also provides valuable insight into the stability and consistency of the learning algorithm. What makes cross-validation particularly valuable is its ability to detect problems like overfitting while making efficient use of limited data. Rather than setting aside a large portion of data exclusively for testing, cross-validation allows every data point to contribute to both training and evaluation at different stages of the process. This approach is especially important when working with small data sets, where every example provides valuable information for learning. The insights gained from cross-validation guide important decisions about model selection, hyperparameter tuning, and algorithm comparison. By providing unbiased estimates of performance across different approaches, cross-validation helps developers choose the most promising techniques before final deployment. As you prepare for peaceful sleep, imagine these careful evaluation processes continuing throughout the night, ensuring that tomorrow's artificial intelligence systems will be reliable, robust, and ready to perform effectively in the complex, unpredictable real world. Concept 21. Convolutional neural networks. Convolutional neural networks represent a revolutionary architectural design specifically crafted for processing visual information, revolutionizing how artificial intelligence systems understand and interpret images. These specialized networks draw inspiration from the visual cortex of biological brains, where neurons respond to specific patterns within limited regions of the visual field. Think of convolutional networks as digital vision systems that examine images through multiple layers of increasingly sophisticated filters, gradually building understanding from simple edges and textures to complex objects and scenes. The fundamental innovation of convolutional networks lies in their use of convolution operations, mathematical processes that systematically scan across images using small filters or kernels. These filters detect specific patterns such as horizontal lines, vertical edges, curves, or color gradients wherever they appear in an image. Unlike traditional neural networks that treat each pixel independently, convolutional networks preserve the spatial relationships between neighboring pixels, maintaining the geometric structure that makes visual information meaningful. The architecture typically consists of alternating convolutional and pooling layers that gradually reduce image dimensions while extracting increasingly abstract features. Early layers might detect simple edges and textures. Middle layers combine these into shapes and patterns, while deeper layers recognize complete objects like faces, vehicles, or animals. This hierarchical feature extraction mirrors how human visual perception progresses from basic sensory input to high-level object recognition. The impact of convolutional neural networks extends far beyond simple image classification. These systems power facial recognition in photographs, enable medical imaging diagnosis, guide autonomous vehicle navigation, and facilitate augmented reality applications. They analyze satellite imagery for environmental monitoring, inspect manufacturing products for quality control, and help astronomers identify celestial objects in telescope data. As you drift into peaceful sleep, imagine these visual processing networks quietly analyzing countless images, helping machines see and understand the world with remarkable clarity and precision. Concept 22. Recurrent neural networks. Recurrent neural networks introduce the crucial element of memory to artificial intelligence systems, enabling them to process sequential information where context and order matter significantly. Unlike traditional neural networks that treat each input independently, recurrent networks maintain internal memory states that allow them to remember previous inputs and use this historical context to inform current decisions. Think of recurrent networks as digital minds with short-term memory, capable of understanding that the meaning of words, events, or data points depends heavily on what came before them. The key architectural feature that distinguishes recurrent networks is their ability to create loops within the network structure, allowing information to flow not only forward through layers, but also backward through time. This creates a form of artificial memory, where the network's current state incorporates information from all previous time steps. When processing a sentence, for example, the network maintains a running summary of what it has seen so far, updating this internal state with each new word while preserving context from earlier parts of the sentence. The applications of recurrent neural networks span any domain where sequential patterns and temporal relationships are important. These systems excel at language translation, where understanding sentence structure and maintaining context across languages is crucial. They power speech recognition systems that must interpret spoken words within the flow of continuous speech, and they enable predictive text systems that suggest completions based on what you have typed so far. Financial analysts use recurrent networks to analyze time series data, identifying trends and patterns that develop over extended periods. Modern variations of recurrent networks include sophisticated memory mechanisms that can maintain relevant information across very long sequences while forgetting irrelevant details. These advances enable systems to understand lengthy documents, maintain coherent conversations, and analyze complex temporal patterns. As you settle into restful sleep, imagine these memory-enabled networks processing streams of sequential information, maintaining context and understanding across time to create more intelligent and contextually aware artificial intelligence systems. Concept 23. Transformer architecture. Transformer architecture represents a groundbreaking paradigm shift in artificial intelligence that revolutionized how machines process and understand sequential information, particularly natural language. This innovative design addresses fundamental limitations of previous approaches by enabling parallel processing of entire sequences while maintaining sophisticated understanding of relationships between distant elements. Think of transformer architecture as creating artificial minds that can simultaneously consider every word in a sentence, paragraph, or even entire document, understanding how each element relates to every other element, regardless of their distance from each other. The revolutionary innovation of transformers lies in their attention mechanism, which allows the system to dynamically focus on the most relevant parts of the input when making decisions about each element. Unlike recurrent networks that process information sequentially, transformers can examine all parts of the input simultaneously, creating rich understanding of context and relationships. This parallel processing capability dramatically improves both training efficiency and the quality of learned representations, enabling much larger and more capable models than were previously feasible. The attention mechanism works by calculating relevant scores between every pair of positions in the input sequence, creating a comprehensive map of how each element should influence the processing of every other element. This creates remarkably flexible and context-sensitive processing, where the same word can have different meanings and importance depending on the surrounding context. The architecture can learn to pay attention to syntactic relationships, semantic connections, and even subtle pragmatic cues that influence meaning. Transformer architecture has become the foundation for the most advanced language models and has been successfully adapted for computer vision, audio processing, and multimodal applications that combine different types of information. These systems power modern language translation, text generation, question answering, and conversational artificial intelligence. As you drift toward peaceful sleep, imagine these attention-based systems simultaneously considering vast amounts of information, creating sophisticated understanding that enables more natural and helpful interactions between humans and artificial intelligence. Concept 24. Attention mechanisms. Attention mechanisms provide artificial intelligence systems with the sophisticated ability to selectively focus on the most relevant information while processing complex inputs, much like how human attention naturally highlights important details while filtering out distractions. This cognitive capability enables AI systems to handle information more efficiently and effectively by dynamically determining which parts of the input deserve the most consideration for each specific decision or prediction. The fundamental principle behind attention mechanisms involves learning to assign importance weights to different parts of the input based on their relevance to the current task or context. When processing a sentence, an attention system might focus heavily on the subject and verb when determining the overall meaning, while giving less weight to articles and prepositions. When analyzing an image, attention might concentrate on objects that are most relevant to the question being asked, effectively ignoring background elements that do not contribute to the answer. The mathematical implementation of attention involves computing similarity or relevance scores between different elements of the input, then using these scores to create weighted combinations that emphasize the most important information. This process is learned automatically during training, allowing the system to discover which types of relationships and patterns are most predictive for the specific tasks it needs to perform. The attention weights themselves often provide valuable insights into how the system makes decisions, creating more interpretable and trustworthy artificial intelligence. Modern attention mechanisms have evolved into sophisticated architectures that can maintain multiple types of attention simultaneously, focusing on different aspects of the input for different purposes. These systems can attend to local details and global patterns simultaneously, maintain attention across very long sequences, and even attend to information across different modalities such as text and images together. As you prepare for restful sleep, imagine these focused artificial minds continuously directing their attention to the most relevant information, creating more efficient and effective processing that enhances the capability of artificial intelligence systems. Concept 25. Generative adversarial networks. Generative adversarial networks introduce a fascinating competitive learning paradigm where two artificial intelligence systems engage in a continuous game of creation and detection, driving each other toward increasingly sophisticated capabilities. This innovative architecture consists of two neural networks locked in an adversarial relationship, a generator that creates synthetic data and a discriminator that attempts to distinguish between real and artificially generated content. Think of this system as a master forger working alongside a detective, where the forger continuously improves at creating convincing fakes, while the detective becomes increasingly skilled at spotting subtle signs of artificial creation. The training process resembles an evolutionary arms race where both networks simultaneously improve their capabilities through competition. The generator begins by creating obviously fake content, while the discriminator easily identifies these crude attempts. However, as training progresses, the generator learns to create increasingly realistic content to fool the discriminator, while the discriminator develops more sophisticated detection capabilities to maintain its accuracy. This competitive pressure drives both systems toward exceptional performance levels that neither could achieve through individual training. The applications of generative adversarial networks span creative and practical domains, demonstrating remarkable versatility in content creation. These systems can generate photorealistic images of people who do not exist, create artwork in specific artistic styles, produce synthetic data for training other machine learning models, and even generate realistic speech or music. In practical applications, they help create training data for scenarios where real data is scarce or expensive to obtain, enable data privacy protection by generating synthetic alternatives to sensitive information, and support creative industries with tools for generating ideas and content. The quality of content produced by modern generative adversarial networks often surpasses human ability to distinguish synthetic from real material, raising important questions about authenticity and verification in digital media. As you settle into peaceful sleep, imagine these creative artificial minds engaged in their perpetual dance of creation and detection, continuously pushing the boundaries of what machines can generate while developing ever more sophisticated understanding of the patterns that define realistic content. Concept 26. Transfer learning. Transfer learning represents an elegant and efficient approach to artificial intelligence development that leverages knowledge gained from one task or domain to accelerate learning in related areas. This technique mirrors the natural human ability to apply skills and knowledge acquired in one context to new but similar situations, such as using bicycle riding skills to learn motorcycle operation more quickly. Think of transfer learning as giving artificial intelligence systems the ability to build upon their previous educational experiences, creating more efficient learning processes that require less data and computational resources for each new challenge. The fundamental principle behind transfer learning recognizes that many artificial intelligence tasks share common underlying patterns and representations, even when their surface characteristics appear different. A neural network trained to recognize objects in photographs develops internal representations that capture edges, textures, shapes, and patterns that remain useful for analyzing medical images, satellite imagery, or artistic works. Rather than starting from scratch for each new application, transfer learning allows systems to begin with sophisticated pre-trained representations and adapt them to new domains. The process typically involves taking a neural network that has been trained on a large, general dataset and fine-tuning it for a specific application with a smaller, specialized dataset. The early layers of the network, which capture fundamental patterns, often remain largely unchanged, while the final layers are adapted to recognize the specific categories or patterns relevant to the new task. This approach dramatically reduces the amount of training data needed for new applications and significantly decreases the computational time required to develop effective systems. Transfer learning has democratized artificial intelligence development by making sophisticated capabilities accessible to organizations and researchers who lack the resources to train large models from scratch. Medical researchers can adapt image recognition systems for diagnostic applications. Environmental scientists can modify satellite imagery systems for new monitoring tasks. And small businesses can customize language models for their specific communication needs. As you drift toward restful sleep, imagine these adaptable artificial minds seamlessly transferring their accumulated wisdom from one domain to another, creating more efficient and accessible artificial intelligence solutions. Concept 27: Ensemble methods. Ensemble methods harness the collective wisdom of multiple artificial intelligence systems working together, creating solutions that surpass what any individual system could achieve alone. This approach draws inspiration from the principle that diverse perspectives and approaches often lead to better decision-making, much like how a panel of experts with different backgrounds can provide more robust insights than any single specialist. Think of ensemble methods as orchestrating a symphony of artificial intelligence systems, where each contributes its unique strengths while the combination produces harmonious and superior performance. The power of ensemble methods lies in their ability to combine different types of errors and biases, allowing the strengths of each individual system to compensate for the weaknesses of others. When multiple systems make predictions about the same problem, their individual errors often cancel out while their correct insights reinforce each other. This statistical phenomenon, known as the wisdom of crowds, enables ensemble systems to achieve remarkable accuracy and robustness even when individual components have modest performance levels. There are several strategies for creating effective ensembles, each with distinct advantages for different types of problems. Bagging methods train multiple versions of the same algorithm on different subsets of the training data, creating diversity through varied training experiences. Boosting methods train systems sequentially, with each new system focusing on correcting the mistakes made by its predecessors. Stacking methods use sophisticated meta-learning approaches to optimally combine predictions from diverse algorithms with complementary strengths. The applications of ensemble methods span virtually every domain of artificial intelligence, from financial risk assessment to medical diagnosis to recommendation systems. These approaches provide improved accuracy, better uncertainty estimation, and increased robustness against unexpected inputs or changing conditions. Modern artificial intelligence competitions are routinely won by ensemble approaches that combine dozens or even hundreds of individual models. As you prepare for peaceful sleep, imagine these collaborative artificial intelligence systems working in harmony, each contributing their unique perspective to create solutions that are more reliable, accurate, and trustworthy than any individual approach could provide. Concept 28: Hyperparameter tuning. Hyperparameter tuning represents the delicate art and systematic science of optimizing the configuration settings that control how artificial intelligence systems learn and operate. These hyperparameters serve as the foundational choices that determine the architecture, learning behavior, and performance characteristics of machine learning models before training begins. Think of hyperparameter tuning as fine-tuning a complex musical instrument, where adjusting various knobs and settings can dramatically influence the quality and character of the final performance, requiring both technical knowledge and intuitive understanding to achieve optimal results. Unlike the parameters that artificial intelligence systems learn during training, hyperparameters must be set by human designers or automated optimization procedures before the learning process begins. These settings include choices about network architecture, such as the number of layers and neurons' learning rates that control how quickly the system adapts. Regularization parameters that prevent overfitting and batch sizes that determine how many examples are processed simultaneously. Each of these decisions influences not only the final performance, but also the training time, memory requirements, and stability of the learning process. The challenge of hyperparameter tuning stems from the complex interactions between different settings and their non-obvious effects on system performance. Changing one hyperparameter often requires adjustments to others to maintain optimal balance, creating a high-dimensional optimization problem where small changes can have dramatic consequences. Traditional approaches involved manual experimentation and expert intuition, but modern methods employ sophisticated search algorithms, Bayesian optimization, and automated machine learning techniques to systematically explore the space of possible configurations. The importance of effective hyperparameter tuning cannot be overstated, as poor choices can render even the most sophisticated algorithms ineffective, while optimal settings can unlock exceptional performance from relatively simple approaches. Modern artificial intelligence development increasingly relies on automated hyperparameter optimization tools that can efficiently search through thousands of potential configurations. As you settle into restful sleep, imagine these patient optimization processes continuing their systematic search through the night, gradually discovering the precise settings that will enable artificial intelligence systems to reach their full potential. Concept 29, Regularization. Regularization encompasses a collection of techniques designed to prevent artificial intelligence systems from becoming overly complex or specialized, helping them maintain the ability to generalize effectively to new situations. These methods address the fundamental tension between learning detailed patterns from training data and maintaining the flexibility needed for good performance on unseen examples. Think of regularization as providing artificial intelligence systems with built-in wisdom about moderation and balance, encouraging them to learn robust and generalizable patterns rather than memorizing specific details that might not apply to new situations. The core principle behind regularization involves adding constraints or penalties to the learning process that discourage overly complex solutions. Just as physical exercise requires progressive overload balanced with adequate recovery, machine learning requires sophisticated pattern recognition balanced with simplicity constraints that prevent overfitting. These techniques work by modifying the optimization objective to include terms that penalize complexity, effectively creating a trade-off between fitting the training data perfectly and maintaining model simplicity. Common regularization techniques include weight decay methods that penalize large parameter values, dropout procedures that randomly deactivate neurons during training to prevent over-reliance on specific pathways, and data augmentation approaches that artificially increase training data diversity through systematic transformations. Each technique addresses different aspects of the overfitting problem, and they are often combined to create comprehensive regularization strategies that work synergistically to improve generalization performance. The benefits of effective regularization extend beyond improved accuracy to include enhanced interpretability, reduced computational requirements, and increased robustness to variations in input data. Regularized models tend to be more stable and predictable in their behavior, making them more suitable for deployment in critical applications where reliability is paramount. Modern deep learning systems routinely employ multiple forms of regularization simultaneously, creating robust learning processes that can handle complex real-world challenges. As you drift toward peaceful sleep, imagine these balanced artificial intelligence systems learning with wisdom and restraint, developing understanding that is both sophisticated and generalizable, equipped to handle the complexity and variability of the real world. Concept 30. Dimensionality reduction. Dimensionality. Reduction represents the sophisticated process of distilling complex high-dimensional information into simpler, more manageable representations while preserving the most important characteristics and relationships within the data. This technique addresses one of the fundamental challenges in artificial intelligence: how to extract meaningful insights from datasets that contain hundreds, thousands, or even millions of variables or features. Think of dimensionality reduction as creating elegant summaries of complex information, much like how a skilled artist can capture the essence of a detailed landscape in a simple sketch that conveys the most important visual elements. The necessity for dimensionality reduction arises from the curse of dimensionality, a phenomenon where traditional analysis methods become ineffective as the number of variables increases. In high-dimensional spaces, data points become increasingly sparse and distant from each other, making it difficult for machine learning algorithms to identify meaningful patterns or relationships. Additionally, high-dimensional datasets often contain redundant or irrelevant information that can confuse learning algorithms and increase computational requirements without providing corresponding benefits in understanding or predictive accuracy. The most fundamental approaches to dimensionality reduction include principal component analysis, which finds the directions of maximum variance in the data and projects information onto these most informative dimensions, and linear discriminant analysis, which identifies dimensions that best separate different categories or classes. More sophisticated non-linear methods such as T-distributed stochastic, neighbor embedding, and autoencoders can capture complex relationships and create representations that preserve intricate patterns while dramatically reducing the number of dimensions required to represent the information. The applications of dimensionality reduction extend throughout artificial intelligence and data science, enabling visualization of complex datasets, improving the efficiency of machine learning algorithms, reducing storage requirements, and facilitating the discovery of hidden patterns and relationships. These techniques are particularly valuable in fields such as genomics, where datasets might contain measurements for tens of thousands of genes, and computer vision, where images contain millions of pixel values that must be processed efficiently. As you prepare for restful sleep, imagine these dimension-reducing systems working quietly through the night, finding elegant and efficient ways to represent the complexity of our information-rich world in forms that artificial intelligence systems can understand and process effectively. Concept 31 Recommendation. Systems recommendation systems represent sophisticated artificial intelligence applications that learn your preferences, interests, and behaviors to suggest content, products, or services you are most likely to enjoy. These systems quietly analyze your digital footprint, from movies you watch to products you purchase, creating personalized profiles that predict your future interests. Think of recommendation systems as thoughtful digital assistants who remember everything you like and continuously search for new discoveries that match your unique tastes. The technology combines multiple approaches, including collaborative filtering, which finds users with similar preferences, and content-based filtering, which analyzes the characteristics of items you have previously enjoyed. Modern systems integrate both approaches with deep learning techniques that can understand complex patterns in user behavior and item attributes. These systems power the personalized experiences you encounter across streaming platforms, online shopping sites, social media feeds, and news applications. They help you discover new music artists, find relevant products among millions of options, and stay informed about topics that interest you most. As you settle into sleep, these recommendation engines continue learning from millions of users, refining their understanding of human preferences to create more satisfying and relevant experiences for tomorrow. Concept 32 Autonomous Vehicles. Autonomous vehicles represent one of the most complex applications of artificial intelligence, integrating computer vision, sensor fusion, predictive modeling, and real-time decision-making to navigate safely through dynamic environments. These vehicles use arrays of cameras, radar, LiDAR, and other sensors to create detailed three-dimensional maps of their surroundings, continuously updating their understanding as conditions change. Think of autonomous vehicles as digital chauffeurs with superhuman perception and reaction capabilities. The artificial intelligence systems process thousands of data points per second, identifying pedestrians, other vehicles, traffic signs, road conditions, and potential hazards while predicting the likely behavior of other road users. Advanced algorithms plan optimal routes, execute precise steering and braking maneuvers, and make split-second decisions that prioritize safety above all other considerations. Modern autonomous vehicles demonstrate varying levels of automation, from driver assistance features that help with parking or highway driving to fully self-driving capabilities in controlled environments. These systems promise to reduce traffic accidents, improve mobility for disabled individuals, and transform urban transportation. As you drift into peaceful sleep, autonomous vehicles continue their cautious journeys through quiet streets, their sensors vigilant, and their artificial minds focused on safe passage through the night. Concept 33. Predictive Analytics. Predictive analytics harnesses the power of artificial intelligence to forecast future events, trends, and behaviors by analyzing historical data patterns and identifying subtle signals that indicate likely outcomes. These systems excel at finding complex relationships within vast datasets that would be impossible for humans to detect manually. Think of predictive analytics as digital fortune tellers that base their insights on mathematical analysis rather than mystical intuition. The technology employs sophisticated machine learning algorithms that learn from historical examples to identify patterns associated with specific outcomes. Weather prediction systems analyze atmospheric data to forecast storms, financial models predict market movements, and healthcare systems identify patients at risk of developing complications. Business applications include demand forecasting for inventory management, customer churn prediction for retention strategies, and risk assessment for insurance and lending decisions. These systems help organizations make more informed decisions, optimize resource allocation, and prepare for future challenges and opportunities. The accuracy of predictive analytics continues improving as more data becomes available and algorithms become more sophisticated. As you rest tonight, predictive systems around the world analyze countless data streams, generating forecasts that will guide important decisions and help humanity prepare for tomorrow's challenges and opportunities. Concept 34. Chatbots and virtual assistants. Chatbots and virtual assistants represent artificial intelligence applications designed to communicate with humans using natural language, providing information, assistance, and companionship through conversational interfaces. These systems combine natural language processing, knowledge databases, and response generation capabilities to create engaging dialogue experiences. Think of them as digital companions who are always available to help, answer questions, or simply provide friendly conversation. Modern virtual assistants can understand context, maintain conversation history, and adapt their responses to individual user preferences and communication styles. They integrate with various services and databases to provide real-time information, complete tasks, and coordinate complex multi-step interactions across different platforms and applications. These systems serve diverse roles, from customer service representatives handling routine inquiries to personal assistants managing schedules and smart home devices. Educational chatbots provide tutoring and support, while healthcare assistants offer symptom checking and appointment scheduling. Entertainment-focused systems engage users with games, stories, and casual conversation. The sophistication of conversational artificial intelligence continues advancing rapidly, with systems becoming increasingly natural and helpful in their interactions. As you prepare for sleep, virtual assistants around the world continue their quiet conversations, providing support and companionship to users across different time zones, always ready to help with questions or simply offer a friendly response to those seeking connection. Concept 35. Medical diagnosis. AI medical diagnosis. AI represents a revolutionary application of artificial intelligence that assists healthcare professionals in identifying diseases, analyzing symptoms, and recommending treatment approaches with unprecedented accuracy and speed. These systems analyze medical images, laboratory results, patient histories, and symptom patterns to provide diagnostic insights that complement human medical expertise. Think of medical AI as tireless digital consultants that never forget medical knowledge and can instantly access vast libraries of case studies and research. The technology excels at pattern recognition tasks that are challenging even for experienced physicians. AI systems can detect early-stage cancers in medical imaging, identify rare genetic disorders from photographs, and analyze complex combinations of symptoms that might indicate uncommon conditions. They process information consistently without fatigue and can consider thousands of possibilities simultaneously. These systems support radiologists in interpreting X-rays, MRIs, and CT scans, help pathologists analyze tissue samples, and assist general practitioners in differential diagnosis. They also enable faster screening programs and bring expert-level analysis to underserved areas with limited access to specialists. The integration of medical AI promises to improve diagnostic accuracy, reduce healthcare costs, and enable earlier detection of serious conditions. As you drift into restful sleep, medical AI systems continue their vigilant work analyzing patient data, supporting healthcare professionals, and contributing to better health outcomes for patients around the world. Concept 36. Fraud detection. Fraud detection systems employ sophisticated artificial intelligence algorithms to identify suspicious patterns, anomalous behaviors, and potential security threats in real time across financial transactions, online activities, and digital interactions. These systems analyze millions of data points simultaneously, comparing current activities against learned patterns of legitimate and fraudulent behavior. Think of fraud detection systems as digital security guards with perfect memory and lightning-fast analysis capabilities. The technology uses machine learning to establish baseline patterns of normal behavior for individuals, organizations, and systems, then flags activities that deviate significantly from these established norms. Advanced systems can detect subtle indicators of fraud that human analysts might overlook, including unusual timing patterns, geographic anomalies, and complex multi-step schemes. Applications span credit card transactions, insurance claims, online account creation, and identity verification. These systems help protect consumers from financial losses, safeguard businesses from costly fraud schemes, and maintain trust in digital commerce platforms. They continuously adapt to new fraud tactics as criminals develop more sophisticated approaches. Modern fraud detection balances security with user experience, minimizing false positives that might inconvenience legitimate users while maintaining high accuracy in identifying genuine threats. As you settle into peaceful sleep, fraud detection systems maintain their constant vigilance, analyzing countless transactions and activities to protect digital assets and personal information throughout the quiet hours of the night. Concept 37. Game playing. Game playing AI demonstrates artificial intelligence capabilities through strategic thinking, long-term planning, and competitive decision-making in complex, rule-based environments. These systems have achieved superhuman performance in games ranging from chess and Go to video games and poker, showcasing different aspects of intelligence including pattern recognition, strategic planning, and adaptive learning. Think of game-playing AI as digital masters who never tire, never lose focus, and can consider millions of possible moves in seconds. The development of game-playing systems has driven significant advances in artificial intelligence research. Chess programs pioneered deep search algorithms, Go systems developed sophisticated pattern recognition and intuitive evaluation, while poker AI mastered imperfect information and strategic deception. Each game presents unique challenges that require different cognitive capabilities. Modern game-playing AI systems use reinforcement learning to improve through self-play, generating millions of games to discover optimal strategies. They often develop novel approaches that surprise human experts and reveal new insights about game theory and strategic thinking. Beyond entertainment, the techniques developed for game-playing AI transfer to real-world applications, including military strategy, business planning, resource allocation, and any domain requiring strategic decision-making under uncertainty. As you drift towards sleep, imagine these strategic artificial minds engaged in endless games, continuously refining their decision-making capabilities and developing insights that enhance artificial intelligence across countless practical applications. Concept 38, Robotics. Robotics represents the physical embodiment of artificial intelligence, combining intelligent software with mechanical systems to create machines capable of perceiving, reasoning about, and manipulating the physical world. These systems integrate multiple AI technologies including computer vision, motion planning, sensor fusion, and control algorithms to perform tasks in real environments. Think of robotics as giving artificial intelligence hands, eyes, and mobility to interact directly with the physical world around us. Modern robotic systems demonstrate remarkable capabilities including precise manufacturing assembly, delicate surgical procedures, autonomous navigation through complex environments, and adaptive responses to unexpected situations. They combine sophisticated sensors with intelligent processing to understand three-dimensional spaces, identify objects, and plan coordinated movements that achieve specific goals. Applications span industrial automation, healthcare assistance, space exploration, disaster response, and domestic help. Robotic systems work alongside humans in collaborative environments, perform dangerous tasks in hazardous conditions, and provide assistance to individuals with mobility limitations or other special needs. The integration of advanced artificial intelligence with robotic platforms continues expanding the possibilities for automated physical assistance and autonomous operation in complex real-world environments. As you prepare for restful sleep, robotic systems around the world continue their quiet work, maintaining industrial processes, assisting healthcare professionals, and exploring environments where human presence would be difficult or impossible, extending human capabilities into every corner of our physical world. Concept 39. Smart Home Technology. Smart Home. Technology integrates artificial intelligence throughout living environments to create responsive, adaptive, and intelligent spaces that anticipate occupant needs and preferences. These systems combine sensors, connected devices, and learning algorithms to optimize comfort, security, energy efficiency, and convenience automatically. Think of smart homes as living spaces that learn your routines and quietly adjust themselves to enhance your daily experience. The artificial intelligence analyzes patterns in occupancy, usage, and preferences to automatically adjust lighting, temperature, security systems, and entertainment devices. Voice-activated assistants serve as central command interfaces, while machine learning algorithms optimize energy consumption and predict maintenance needs for various home systems. Modern smart home systems can detect unusual activities that might indicate security concerns, adjust environmental conditions based on weather forecasts and personal schedules, and coordinate multiple devices to create seamless experiences. They learn from occupant behavior to become increasingly helpful and efficient over time. Integration with external services enables smart homes to coordinate with utility grids, emergency services, and delivery systems to create comprehensive connected living experiences. These systems promise increased comfort, reduced energy consumption, and enhanced security for residents. As you settle into sleep in your possibly smart-enabled home, artificial intelligence systems may be quietly monitoring and adjusting your environment, ensuring optimal conditions for restful sleep while learning your preferences for tomorrow's automated assistants. Concept 40. Financial trading algorithms. Financial trading algorithms represent sophisticated artificial intelligence applications that analyze market data, identify trading opportunities, and execute investment decisions at speeds and scales impossible for human traders. These systems process vast amounts of financial information, including price movements, news events, economic indicators, and market sentiment to make split-second trading decisions. Think of trading algorithms as digital investment managers with perfect memory, lightning-fast reflexes, and the ability to monitor thousands of markets simultaneously. The technology employs machine learning to identify patterns in market behavior, predict price movements, and optimize trading strategies based on historical performance and current conditions. Advanced systems can adapt to changing market conditions, learn from successful and unsuccessful trades, and adjust their approaches accordingly. These algorithms execute various strategies, including high-frequency trading that capitalizes on tiny price differences, algorithmic portfolio management that maintains optimal asset allocation, and quantitative analysis that identifies undervalued securities. They help institutional investors manage risk, improve execution efficiency, and discover trading opportunities that human analysts might miss. The impact of algorithmic trading extends throughout financial markets, providing liquidity, improving price discovery, and enabling more efficient capital allocation. Modern markets rely heavily on these intelligent systems to process the enormous volume of transactions that occur every second. As you drift into peaceful sleep, trading algorithms continue their relentless analysis of global markets, making countless micro-decisions that help maintain the flow of capital and commerce that underpins the modern economy. Concept 41. AI ethics. AI ethics encompasses the moral principles, values, and guidelines that govern the development, deployment, and use of artificial intelligence systems to ensure they benefit humanity while avoiding potential harms. This field addresses fundamental questions about fairness, accountability, transparency, and the broader societal implications of increasingly powerful artificial intelligence technologies. Think of AI ethics as the moral compass that guides the development of artificial intelligence toward outcomes that align with human values and social good. Key ethical considerations include ensuring AI systems treat all individuals fairly regardless of race, gender, or background, maintaining human agency and control over important decisions, protecting privacy and personal data, and preventing the misuse of AI capabilities for harmful purposes. These principles require careful consideration during every stage of AI development and deployment. The challenge of AI ethics involves balancing innovation with responsibility, ensuring that the benefits of artificial intelligence are distributed equitably while minimizing risks to individuals and society. This includes addressing concerns about job displacement, surveillance, autonomous weapons, and the concentration of AI power among large corporations or governments. Ethical AI development requires collaboration between technologists, policymakers, ethicists, and diverse stakeholders to establish standards, regulations, and best practices that guide responsible innovation. As you rest tonight, consider how the ethical frameworks we establish today will shape the artificial intelligence systems of tomorrow, ensuring they serve humanity's best interests while respecting fundamental human rights and values. Concept 42. Bias in AI. Bias in AI represents one of the most significant challenges facing artificial intelligence development, occurring when systems perpetuate, amplify, or create unfair advantages or disadvantages for certain groups of people. These biases can emerge from training data, algorithmic design choices, or deployment contexts, leading to discriminatory outcomes that reinforce existing social inequalities. Think of AI bias as digital prejudices that can inadvertently encode unfair assumptions into seemingly objective technological systems. Common sources of bias include historical data that reflects past discrimination, unrepresentative datasets that exclude certain populations, and evaluation metrics that prioritize some outcomes over others. These biases can manifest in hiring algorithms that favor certain demographics, facial recognition systems that perform poorly on darker skin tones, and lending systems that discriminate against specific communities. Addressing AI bias requires diverse development teams, comprehensive testing across different populations, ongoing monitoring of system performance, and active efforts to identify and correct unfair outcomes. This includes developing fairness metrics, implementing bias detection tools, and creating inclusive datasets that represent the full diversity of people affected by AI systems. The importance of addressing bias extends beyond technical considerations to fundamental questions of justice and equality in an increasingly AI-driven world. Biased AI systems can perpetuate discrimination at scale, affecting millions of people in areas including employment, criminal justice, healthcare, and financial services. As you drift towards sleep, remember that creating fair and unbiased AI systems requires continuous vigilance and commitment to equity, ensuring that artificial intelligence serves all members of society fairly and justly. Concept 43: Explainable AI. Explainable AI addresses the critical need for artificial intelligence systems to provide clear, understandable explanations for their decisions and recommendations, especially in high-stakes applications where transparency is essential for trust and accountability. This field develops methods to make complex AI systems interpretable to humans, bridging the gap between powerful but opaque algorithms and the human need to understand automated decisions. Think of explainable AI as creating digital transparency that allows us to peek inside the black box of artificial intelligence decision-making. The challenge arises because many powerful AI systems, particularly deep learning networks, make decisions through complex mathematical processes that are difficult for humans to interpret. While these systems may achieve exceptional accuracy, their decision-making process remains mysterious, making it difficult to verify their reasoning or identify potential errors. Explainable AI techniques include generating visualizations that highlight important input features, providing natural language explanations for decisions, creating simplified models that approximate complex system behavior, and developing inherently interpretable algorithms that balance performance with transparency. Applications are particularly important in healthcare diagnosis, financial lending, criminal justice, and autonomous vehicles, where understanding the reasoning behind AI decisions is crucial for safety, fairness, and regulatory compliance. Legal and ethical requirements increasingly demand that AI systems provide explanations for their decisions, especially when they affect human lives. As you settle into restful sleep, researchers continue developing new approaches to make artificial intelligence more transparent and accountable, ensuring that these powerful systems can be understood and trusted by the humans they serve. Concept 44: AI safety. AI safety encompasses the comprehensive efforts to ensure that artificial intelligence systems operate reliably, predictably, and beneficially, particularly as these systems become more powerful and autonomous. This field addresses both immediate concerns about current AI systems and long-term considerations about advanced artificial intelligence that might surpass human cognitive abilities. Think of AI safety as building guardrails and safety mechanisms that protect humanity while allowing artificial intelligence to flourish and contribute positively to society. Current AI safety research focuses on robustness, ensuring systems perform reliably under unexpected conditions, alignment, making sure AI goals match human intentions, and control, maintaining meaningful human oversight over AI decision-making. These efforts include testing systems extensively, implementing fail-safe mechanisms, and designing architectures that remain controllable even as they become more capable. Long-term AI safety considerations address the possibility of artificial general intelligence and superintelligence, exploring how to maintain beneficial outcomes as AI capabilities potentially exceed human intelligence. This includes research into value alignment, ensuring advanced AI systems understand and pursue human values, and governance structures that manage powerful AI development responsibly. The importance of AI safety grows with the increasing influence of artificial intelligence across critical infrastructure, autonomous systems, and decision-making processes that affect millions of people. Safety research aims to prevent accidents, misuse, and unintended consequences while preserving the tremendous benefits that AI can provide. As you drift into peaceful sleep, AI safety researchers work diligently to ensure that artificial intelligence remains a positive force, developing the frameworks and technologies needed to navigate safely toward a future enhanced by beneficial artificial intelligence. Concept 45. Privacy in AI. Privacy in AI addresses the complex challenges of protecting personal information and maintaining individual privacy rights in an era where artificial intelligence systems require vast amounts of data to function effectively. This field explores techniques for training powerful AI systems while minimizing privacy risks, ensuring that the benefits of artificial intelligence do not come at the cost of personal privacy and data security. Think of privacy-preserving AI as creating digital shields that protect personal information while still allowing artificial intelligence to learn and provide valuable services. Key privacy concerns include the collection, storage, and use of personal data for AI training, the potential for AI systems to infer sensitive information from seemingly innocent data, and the risk of re-identifying individuals from anonymized datasets. Modern AI systems often require detailed personal information to provide personalized services, creating tension between functionality and privacy protection. Technical approaches to privacy-preserving AI include differential privacy, which adds carefully calibrated noise to data to protect individual privacy while maintaining statistical utility, federated learning, which trains AI models without centralizing sensitive data, and homomorphic encryption, which enables computation on encrypted data without decryption. Regulatory frameworks such as GDPR and emerging AI governance policies establish legal requirements for privacy protection in AI systems, including rights to explanation, data portability, and the ability to opt out of automated decision-making. The challenge involves balancing innovation with privacy protection, ensuring that advancing AI capabilities do not erode fundamental privacy rights. As you rest tonight, privacy-preserving technologies work quietly to protect personal information while enabling artificial intelligence systems to continue learning and improving in ways that respect individual privacy and maintain public trust. Concept 46. Artificial General Intelligence. Artificial general intelligence represents the theoretical achievement of creating AI systems with human-level cognitive abilities across all domains of knowledge and reasoning, rather than the narrow specialization that characterizes current artificial intelligence applications. AGI would possess the flexibility, creativity, and general problem-solving capabilities that allow humans to learn new skills, adapt to novel situations, and transfer knowledge between different domains. Think of AGI as creating digital minds that match human intellectual versatility and adaptability. Current AI systems excel in specific domains but lack the broad understanding and flexible reasoning that characterizes human intelligence. AGI would bridge this gap, creating systems capable of learning new tasks quickly, understanding context and nuance, engaging in creative problem-solving, and demonstrating common-sense reasoning across diverse situations. The timeline for achieving AGI remains highly uncertain, with expert predictions ranging from decades to potentially much longer. Key challenges include developing systems that can learn efficiently from limited examples, understanding causality and common sense, maintaining coherent goals and values across diverse situations, and integrating multiple types of reasoning and knowledge. The potential impact of AGI could be transformative, affecting every aspect of human society from scientific research and technological development to economic systems and social structures. This prospect raises important questions about safety, control, and the relationship between human and artificial intelligence. As you drift towards sleep, researchers continue working on the fundamental problems that might eventually lead to artificial general intelligence, while carefully considering the profound implications such technology would have for humanity's future. Concept 47, the singularity. The singularity represents a hypothetical point in future technological development where artificial intelligence becomes capable of recursive self-improvement, leading to rapid, exponential advances that could fundamentally transform human civilization. This concept suggests that once AI systems become intelligent enough to improve their own design, they could trigger an acceleration of technological progress beyond human ability to predict or control. Think of the singularity as a potential technological event horizon beyond which the future becomes fundamentally unpredictable. The concept builds on the observation that technological progress often follows exponential patterns, with each advancement enabling faster subsequent advances. Applied to artificial intelligence, this suggests that sufficiently advanced AI could improve itself at an accelerating pace, potentially leading to superintelligence that vastly exceeds human cognitive abilities across all domains. Proposed timelines for the singularity vary widely among experts and futurists, with some predicting it could occur within decades, while others remain skeptical about whether such rapid, recursive improvement is feasible or even possible. The uncertainty stems from our limited understanding of intelligence, consciousness, and the practical challenges of self-modifying systems. The potential implications of the singularity range from utopian visions of solved global problems and unprecedented prosperity to concerns about human irrelevance or existential risks from uncontrolled superintelligence. This has sparked important discussions about AI safety, human enhancement, and strategies for managing transformative technological change. As you settle into restful sleep, consider how this speculative but profound concept continues to influence AI research priorities and long-term planning for humanity's technological future. Concept 48, Human-AI Collaboration. Human-AI collaboration represents the emerging paradigm where artificial intelligence systems work alongside humans as partners rather than replacements, combining human creativity, intuition, and contextual understanding with AI capabilities in processing, analysis, and pattern recognition. This approach leverages the unique strengths of both human and artificial intelligence to achieve outcomes that neither could accomplish alone. Think of human-AI collaboration as creating powerful partnerships where human wisdom guides artificial intelligence capabilities toward meaningful and beneficial outcomes. Successful collaboration requires designing AI systems that complement human capabilities rather than simply automating human tasks. This includes AI that can explain its reasoning, accept human feedback, and adapt to human preferences and working styles. The goal is creating seamless partnerships where humans and AI systems communicate effectively and work toward shared objectives. Applications span creative industries where AI assists with design and content generation, scientific research where AI helps analyze complex data while humans provide insight and interpretation, healthcare where AI supports diagnosis while doctors maintain responsibility for patient care, and education where AI personalizes learning while teachers provide mentorship and emotional support. The future of work likely involves extensive human-AI collaboration rather than wholesale replacement of human workers. This transformation requires developing new skills for working effectively with AI systems, redesigning workflows to optimize human-AI partnerships, and creating policies that support workers through technological transitions. As you drift into peaceful sleep, Imagine the collaborative partnerships forming between humans and artificial intelligence, combining the best of human insight and artificial intelligence capability to solve complex problems and create innovations that benefit all of humanity. Concept 49: AI governance. AI governance encompasses the policies, regulations, standards, and institutional frameworks needed to guide the responsible development, deployment, and use of artificial intelligence technologies. This field addresses how societies can harness the benefits of AI while managing risks, ensuring accountability, and maintaining democratic values and human rights in an increasingly AI-influenced world. Think of AI governance as creating the rules of the road for artificial intelligence, ensuring that this powerful technology serves the common good. Key governance challenges include establishing safety standards for AI systems, ensuring algorithmic transparency and accountability, protecting privacy and civil liberties, preventing discriminatory outcomes, and managing the economic impacts of automation. These issues require coordination between governments, technology companies, civil society organizations, and international bodies. Governance approaches vary globally, with different countries and regions developing distinct regulatory frameworks that reflect their values, priorities, and institutional capabilities. Some emphasize innovation and industry self-regulation, while others focus on strict oversight and public control of AI development and deployment. International cooperation becomes increasingly important as AI technologies cross borders and global challenges require coordinated responses. This includes developing shared standards, coordinating research priorities, and ensuring that AI governance frameworks support beneficial outcomes for all humanity rather than exacerbating global inequalities. As you rest tonight, policymakers and stakeholders around the world continue working to develop governance frameworks that will shape how artificial intelligence integrates into society, striving to create systems that protect human welfare while enabling beneficial innovation. Concept 50: the future of work. The future of work explores how artificial intelligence will transform employment, job requirements, and economic structures as automation capabilities expand across industries and occupations. This transformation involves both challenges and opportunities, requiring adaptations in education, training, social policies, and economic systems to ensure that AI advancement benefits workers and society broadly. Think of the future of work as navigating a fundamental shift in the relationship between human labor and technological capability. AI automation will likely eliminate some jobs while creating others, transform existing roles by changing required skills, and enable new forms of work that leverage human-AI collaboration. The transition affects different sectors and skill levels differently, with routine and predictable tasks most susceptible to automation, while creative, interpersonal, and complex problem-solving work remains more distinctly human. Preparing for this future requires emphasis on lifelong learning, developing uniquely human skills such as creativity and emotional intelligence, and creating social safety nets that support workers through transitions. Educational systems must evolve to prepare students for AI-augmented careers, while retraining programs help existing workers adapt to changing requirements. Policy considerations include exploring concepts like universal basic income, revising tax structures to account for automated production, and ensuring that AI-driven productivity gains translate into broadly shared prosperity rather than increased inequality. The goal is managing this transition in ways that enhance human flourishing while harnessing AI capabilities for societal benefit. As you drift into final peaceful sleep, reflect on how thoughtful preparation and wise policy choices can help create a future where artificial intelligence enhances human potential and creates meaningful opportunities for fulfilling work and prosperity for all.